everyone. Well, welcome back. Today we're going to continue our discussion of HR diagrams. So our lesson objectives is we're going to review, since we already talked a little bit about it in the last lesson, what an HR diagram is, how we make one, and identify where stars tend to fall on it, and then start classifying stars by where they sit on the HR diagram and talk a little bit about the different sorts of stars. We're also going to focus in on that thing I mentioned in the last lesson, the main sequence. Now, I told you that if you know a star's spectral type and you know it's on the main sequence, you can figure out how bright it is, or rather how luminous it is, how bright it really is rather than how bright it looks, which can get you a distance. So we're going to talk about why the main sequence exists. So here's another HR diagram. And this is a little bit more like how an astronomer would plot it rather than how your textbooks like to plot it. So just to review, we have luminosity going upward from the top, or from the bottom to the top. So bright stars are at the top, faint stars are at the bottom. We have temperature running to the left. Hot stars are on the left, cool stars are on the right. And originally this is basically because we measured it by how red a star was. So blue stars were on the left, red stars are on the right. And each star is plotted as a point. Now this one is nearby bright stars. So there were a few stars that were pretty much, plotting right on top of one another. So in those cases, the point color was changed to show that this represented multiple stars. So that kind of region of green and yellow and red is just saying there's a lot of stars here. Now I want you to look at this diagram and what do you notice? In particular, what are the patterns here? So if we only look at nearby stars, this is kind of a just random sample of stars in our neighborhood of a certain brightness. So of a certain apparent magnitude. Now you can see that most of them were on that main sequence, which I've highlighted in red. That they run on a line from upper left to lower right. And it's not a perfectly straight line, but it's still clearly a line. And it's got some width. Now, what is this? Well, it turns out, again, most stars in our neighborhood fall on this. This represents stars that are neither being born or dying. They're just turning hydrogen into helium, like our sun. And this is what a star spends most of its life on. That's why the main sequence is so full of stars, is because most of a star's life is spent on the main sequence. So let's look at some main sequence stars. And this is a scale model, not real pictures. So you can see at the left, we have Jupiter, a planet for scale. We've already kind of gone through the solar system scale, so we know roughly how big Jupiter is. And then we have 3 main sequence stars. Notice they're all luminosity class V. We have an M class main sequence star, Wolf 359. We have a G class main sequence star, our sun, and we have an A class main sequence star, Sirius. And you can see from their colors that that's kind of in order of temperature. Now the numbers you see in between the letter and the Roman numeral 5, the V, those numbers are subdivisions of our spectral types. So for instance, if we want to be more precise than say a star is a G-type star, we can say, okay, we're going to divide this into 10 bins. G0 is the hottest G-type star, it's almost an F-type. G9 is the coolest G-type star, it's almost a K-type. So our sun is G2, which means it's more like an F-type than a K-type. Sirius is A1. It's more like a B-type than an F-type. Wolf 359 is M7. It is not very much like a K-type. And you can also see the order that the cool main sequence stars are small and large, they're only a little bit bigger than Jupiter, and hotter main sequence stars are bigger. They're maybe a few times the size of the sun. So, all right, that's what we get from the main sequence. And that's where most of the stars we find in our neighborhood are. But we also notice there's a bunch of stars over, kind of coming off the diagram to the upper right. We call that the giant branch, because it kind of looks like it's branching off the main sequence on this HR diagram. And these stars are called red giant stars because they are bigger than main sequence stars and they are red. They tend to be pretty red. You notice they're on the right side of the diagram, which means they're cool red stars. And these are luminosity class 3 stars. So let's look at some sizes for these ones. So they're just like we had Jupiter for scale on this picture. Now we have Sirius for scale, well, the largest of the last stars. And now we have a sampling of some red giant stars. And you can see Pollux, Arcturus, and Aldebaran. They're all class 3. You can see these are quite big. No wonder we call them giants. And they have to be because they're very cool, so they're less luminous per square meter of star, but they're really bright. They're much brighter than the main sequence. So they must be big. They have to. You can see there's some variations between sizes. Now, all of these are bright stars that we can see in our night sky. Okay, so let's switch diagrams from the nearby star plot we had that just grabbed all the nearby stars of certain apparent magnitude and plotted them to one that was more kind of judicious. We've picked a bunch of stars to show off different features of the HR diagram, which includes putting in some fainter stars that were on the previous picture and some rarer stars that were not captured in the previous picture. So here's our kind of diagram in the textbook. Now, one thing I do want to point out before we move on to some of those rarer categories is most main sequence stars are red dwarfs. They are at the lower right. We didn't get as many in the previous picture because they're really faint. Notice they're sitting down at the bottom of the diagram. And as we saw in the picture of Wolf 359, they're faint. They're small. They're faint because they're both cool and small. So 40% of all the stars within 5 parsecs of us are M-type main sequence stars, are red dwarfs. And most of the rest are K-type. So you could still call them kind of red dwarf adjacent. So, all right, so that's just a caveat to the main sequence. Now let's look at some other stars we didn't see on the previous diagram, either because they're rare or faint. We didn't see many red dwarfs because they're faint. Now, let's look at some stars that are really bright, but we don't see that many of because they're really rare. And we call these stars supergiants. They're sitting up here at the top of the diagram, to the right of the main sequence, and just kind of a strip of them. These are the luminosity class 1 stars. These are the brightest sorts of stars of their spectral type. They're very rare, so we didn't see them on the previous picture, but since they're very bright, we can see them from a long distance. So let's look at some supergiants. So again, we're going by using the largest star in the previous image as the first scale. So we have a red giant Aldebaran right there. And it's next to a blue supergiant called Rigel. Rigel is one of the stars in Orion. And it's class 1, and it's a B-type star, so it's pretty hot. And it's not that much bigger than a red giant. But where you get the biggest kinds of stars is you get the red supergiants. You have Antares and Betelgeuse here. Rigel and Betelgeuse are about the same distance from Earth, and they're about the same apparent brightness. So they're probably about the same absolute brightness. But you notice Betelgeuse is huge. Antares is slightly smaller, but still huge. These stars are not just the width of a sun. These are or a width of a planet. These are the width of a planet's orbit. You could stick the entire inner solar system in Betelgeuse out to like Jupiter. That's why they're so bright, even though they're really, really cool stars. So, all right, let's look at more. So another type of faint star we didn't see on the previous diagram, despite them being pretty common, are what are called white dwarfs. White dwarfs are very hot and very small. So they're hot, so we know that like a square meter of white dwarf has to be really bright, but they're really faint, so they have to be tiny stars. Now, they're plotted on this diagram because we can measure their temperatures, but we tend to classify them as their own kind of type because they have different compositions from most of the other stars on this diagram. We're going to talk more about what a white dwarf is when we get to stellar evolution. So the main sequence of stars living their lives, and that includes the red dwarfs. The red giants and the supergiants are stars on their way out, on their dying stars. White dwarfs are kind of dead stars. So the nearest white dwarf to us is Sirius B. Sirius B is called that because it orbits Sirius A, which is the bright star in the picture. Sirius B is the faint star. Now, they're about the same temperature, but because Sirius B is so much fainter, we know it has to be tiny compared to Sirius A. And, you know, about 6% of our neighbors are white dwarfs. So there are 4 within about 5 parsecs. So, all right, we can estimate their sizes if we assume they're black bodies. And what we get is that white dwarfs are about the size of the Earth in terms of their radius. But their masses, which we're going to talk about how we find that later, are comparable to the sun. And that means they have really, really intense gravity. You know, they are taking something the size of our sun and packing it into something the size of the Earth. And remember, the Earth has about a hundredth of the radius of the sun. So as a result, while many things get bigger if you add more stuff, white dwarfs get smaller. And there's still a few things that are missing that we're going to talk about. White dwarfs are, like I said, they're dead stars. They're what happens at the end of a star's life. But there are other more exotic ways a star can end its life. And that leads to objects called neutron stars and black holes. They don't really fit on this diagram because, well, one, black holes don't really have a well-defined surface temperature or luminosity. And neutron stars are sufficiently small, they don't really have an easy measurable luminosity either. And there's one more thing, which is get to the question of what happens when what makes a star a star? What makes a star not a planet? In our solar system, that's a pretty easy divide. The sun is huge, it's burning hydrogen into helium. Jupiter is much smaller compared to the sun, which is the only context in which I can say Jupiter is small. It's not doing any nuclear fusion. But there's some kind of, what are called intermediate objects, something that's too big to be considered a planet and too small to be considered a star. And we call them brown dwarfs. Now, where you'd put them on the diagram would be below and to the right of red dwarfs, but since they're not turning hydrogen into helium, they don't have a well-defined main sequence. The main sequence ends at red dwarfs, at the smallest, tiniest red dwarf that's able to turn hydrogen into helium. So let's talk a little bit about brown dwarfs. So in the late 20th century, astronomers started finding them. They're really faint and small, so we didn't find them earlier. And in particular, they're faint and small, and they're also cool. So they're not very, so that's why they're faint, but it also means they're brightest. Their peak wavelength is in the infrared. We can't see from the surface of Earth that way as well. So we started finding these little faint things. The first one, Gliese 229b, is orbiting a red dwarf, Gliese 229a. And it's based on how bright it is and what temperatures it is. It's too small to be powering itself by turning hydrogen to helium. There's just not enough pressure in the core to get that going. So they don't fit on the main sequence. But they can look really star-like in terms of spectral type. They just look like the natural successor of what something cooler than an M star is, what something cooler than a red dwarf is. So astronomers came up with these new spectral types, L, T, Y. And we called them brown dwarfs because didn't really have a good name for something that's redder than a red dwarf. So here is so back there, that was a picture of Gliese 229b. And it's relatively large. Gliese 229b is about 20 to 50 Jupiter masses, and the smallest a star can be is about 80 Jupiter masses. So this is maybe a third to a half of the size or the mass of the smallest stars. And as we survey our neighborhood looking for faint things that are brightest in the infrared, we find more and more of these brown dwarfs. We can't see them very far out because they're really faint, but we can find them. So this is lumen 16. It is infrared picture, so the colors are kind of funny. We're looking in the infrared, so here all stars look blue because they are brightest at visible wavelengths, which are bluer than infrared. You can see that one of the lumen 16 objects really stands out because it's not blue. It is cool enough that in these wavelengths it looks yellow. Or rather, it looks yellow in the picture, which is based on infrared wavelengths. And both of these are around 30 Jupiter masses, so maybe a a third the minimum mass of a star. And the neat thing is, as we find these fainter and fainter, we find smaller and smaller objects. We start to get things that don't really look like stars much anymore. They look more like what would Jupiter would look like if it wasn't lit by the sun. They start to look more like planets. And officially, the dividing line is about 13 Jupiter masses, where above that is a brown dwarf, below that is a planet. But it's not a nice straightforward line. Some of these planet mass objects might have formed like stars, so we could consider them brown dwarfs. So here is a list of the nearby stars by type. So there's our sun, G2. The Oort cloud is, remember, the big cloud of comets that surrounds our sun. So it's kind of the largest possible extent of the solar system. And it goes pretty far out, maybe a light year. And you see Alpha Centauri. It's a triple star system. The stars are G2, K1, and M5. M5 is called, the M5 Alpha Centauri star is called Proxima Centauri because it's slightly closer than the other two. And the other two are pretty close to one another, so we just drew them as one star. And Alpha Centauri is visible to your unaided eye. So we've known about it for a while. We finally got a distance in 1839. So it was one of the earliest stars we measured. Then you have Barnard star. It's the second one out. It's much fainter. It's another red dwarf like Proxima Centauri, and we didn't get its distance till 1916. And then we have the next two closest stars to our sun don't really have nice names. They're named Ys and then a catalog number because there's nothing really singling them out besides that they happen to be really close to the sun, or really close to the sun in cosmic terms. And notice the dates there, 2013 and 2014. We didn't know about these stars, or these brown dwarfs, until less than a decade ago, because they are all really faint. You have a L type, a T type, and a Y type. In fact, Y is 0855-0714, and that's not its full name, that's the short form, is maybe only 3 to 10 times the mass of Jupiter, and probably about the radius of Jupiter. So it's kind of marginal whether or not you'd even consider that a brown dwarf rather than a planet. So we are definitely going to find more brown dwarfs in our neighborhood, especially the small ones, because they're really hard to see even today. So in summary, we have this HR diagram. It's how we classify stars, because different kinds of stars sit on different places in the diagram. Red giants live in the upper right. White dwarfs live in the lower left. Supergiants are at the far top. The main sequence is that big line from upper left to lower right. This is where the adult stars live. That's why most stars are on the main sequence, because they spend most of their lives being normal adult stars turning hydrogen into helium. There are also these brown dwarfs, which are kind of objects that don't go on the HR diagram because they're not really stars, but they're not really planets. They're kind of an intermediate because nature hates straight lines. All right, next time we are talking about binaries. How do I know how all these star masses, or how do we know? And that gets us to a related topic, which are exoplanets, planets that orbit other stars, because a lot of the ways we study them are the same ways we study binary stars. All right, I'll see everyone next week.